The main objective today is going to be exposing you all to a couple more applications of the normal distribution. So we started by talking about the standard normal distribution. Oh, no. Let me back up, though. Okay, this is more along the lines of homework. So as you're working the homework problems, I'd like to remind you all of a couple of things. In particular, for distributions like the binomial and Poisson distribution, we have some formulas. Okay, so like the binomial distribution was really just there were three important formulas for the binomial distribution. One was that the probability of x yes outcomes, whatever that is. When you do in trials or in experiments, is equal to n factorial over x factorial times n minus x factorial, p to the power of x, 1 minus p to the power of n minus x, was a formula for calculating probabilities. But there were also a couple other formulas that I briefly mentioned. One is we can calculate the expected value of the variable as n times p. Another is that we can calculate the variance in the variable. Like we have a formula that tells us that whatever type of binomial distribution we're working with, the variance in x will be n times p times 1 minus p. Okay, so I just wanted to refresh you all on this. And when you're doing your homework problems, you're not going to, I think there might be some homework problems that ask you to calculate expected value or variance for the binomial distribution. But here's something I want to mention. When you're doing a homework question, when it asks what's the probability, of x equals, and then it gives you several values. Like, what is the probability that x is less than 3? Probability x less than 3, right? That's telling you several values. X could be 0 or 1 or 2. Well, the way to think of that is, or to calculate that, is by adding up the individual numbers. So probability of 0 plus a probability of 1 plus a probability of 2. So that covers all the values that we're discussing, right? Like the several values, the multiple values. Does that make sense? Okay, now another thing though is sometimes you encounter a question where it might be easier to solve for the opposite of what the question asks for. What if the question asked you, what's the probability that x is greater than or equal to, 2? Well, in principle, the way to do that is find the probability x is 2. And then add to that the probability x is equal to 3. And add to that, keep going until you get to the probability that x is equal to n, the last possible value. That's one way you can do it. But sometimes it's easier to think about flipping that around. And you're like, oh, well, the probability x is greater than or equal to 2 is 1 minus the probability that it isn't, right? 1 minus the probability that x is less than 2. And then it's like 1 minus probability, let me put some parentheses around this, like 1 minus the probability of 0 plus the probability of 1. Does that make sense? Right? So this is just something to keep in mind. Like earlier when we talked about probability theory, I said one of the tools that we can use to solve questions is the complement rule. Sometimes instead of solving the question directly as it's posed, it's easier to solve for the opposite, right? Something that's easier than solving for x greater than or equal to 2, if that involves adding up a whole bunch of values. Maybe it's simpler just to do 1 minus and then the opposite, right? The complement. Okay, so y'all follow on this? This suggestion? Okay, so we met the binomial distribution, and I'll mention this trick. Sometimes you want to solve for the opposite is useful with a binomial distribution. The next distribution we came to was Poisson distribution. And the Poisson, okay, by the way, this is called Poisson. It's French. My French is not good. If you want to call it the Poisson distribution, that's fine with me. But the Poisson distribution had a different set of formulas and the probability of X events. So remember, the Poisson distribution was for calculating the number of events that occur within some time period. It's always restricted by the time period. So get this, like if you're trying to sort out a word problem and you're trying to figure out which distribution to use, there's going to be kind of a limiting factor in the question. If the limit is the number of customers who are potentially one way or another, like if you're limited by the number, the maximum number, that sounds like binomial. But if you hear something about time in the question, that's a signal that it's probably Poisson. Okay, if it seems like the number of events in a time period. And for the Poisson distribution, we had a formula to calculate the probability of X events was mu to the power of negative X mu to the power of all of a sudden I'm blanking. Just a second. Okay, so mu to the power of X e to the power of negative mu over X factorial. Okay, and we had a formula for the expected value of X, or rather, the expected value of X is simply that mu value that we're using. But the other thing is the variance in X will also equal mu. Okay, so this is something to keep in mind. Now, when you are solving a question for the Poisson distribution, and the question asks, what is the probability that X is greater than some value, 4? You cannot actually calculate that directly, because that would mean you have to calculate the probability that X is 5 plus the probability that X is 6 plus the probability that X is 7, and you have to keep going and going and going indefinitely, because in principle, 1,000 events could occur within the time period, or 1 billion events. The chance is tiny, 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 but there is still a chance. So that technique, actually adding up all the values greater than 4, doesn't work. The only way to approach this question is instead to do 1 minus the probability that X is less than or equal to 4. So that's 1 minus, then probability that x is 0, plus a probability x is 1, plus a probability x is 3, plus a probability x is 4. Okay, so it must be done that way for the Poisson distribution. If you want to know the probability of greater than, you must flip it around into the complement, like the opposite question, and solve for that. Okay. So these relate to the homework, but they also relate to what we're doing in class today. We've talked for the past couple of classes about first the standard normal distribution. Okay. Standard normal distribution is the one that we actually use for most of our calculations. We try to convert things into something that has a standard normal distribution, because then we can look up the probabilities for the standard normal distribution. However, the standard normal distribution is not what we see most of the time. We see other normal distributions with different means, different variances. So then we talked about normal distributions in general. Okay. Okay, now I want to move into another topic, which are distributions that are approximately normal. So that's going to be today. Okay, and the two distributions that I'll address are the binomial distribution and the Poisson distribution. Both of them become approximately normal. So, okay, let me talk about this binomial distribution first. And, okay, so remember that the binomial setup is like you attempt the same experiment n times with a probability p chance of what I call a yes outcome on each. Okay, x is the total number of yeses from these n experiments. Okay, so here's the deal. As n gets large, x is approximately normal. As a matter of fact, this is the way that the normal distribution was first envisioned, as kind of the limit of a bunch of binomial experiments. Okay, let me show you all something. Okay, it's a YouTube video showing an example of something called a Galton board. Okay, so let me explain this Galton board. The way that a Galton board looks has a bunch of pegs that are set up kind of off-center in a triangle. This was invented by a statistician named Francis Galton. I mentioned him earlier in the class as a cousin of Charles Darwin, but also the father of modern statistics. So he invented this thing, this device, where you drop a marble or a ball down a chute, okay? And as it falls, it hits a bunch of pegs. And every time it hits a peg, it has to decide whether to bounce left or right. Or at least, I mean, it randomly bounces left or right. And then left or right again, and again, and again, and again, until the ball finally falls in some position. Okay, and so Galton's point was, if you do this for lots and lots and lots of balls, it should be the case that they fall down and form essentially a normal distribution. Okay, so let me show you all some Galton boards on YouTube. So imagine we did have a binomial situation that's with fairly large numbers. Let's imagine that a pollster calls n equals 100 people and asks if they favor some candidate. Okay, now let's suppose that 60% of the population favors the candidate. Okay. So that means if I were to call a randomly selected person from the population, there's a 60% chance that the person will say that they intend to vote for the candidate, right? So here's my p equals 0.6. Okay, but the pollster might wonder, what's the probability that x is less than 50? Okay, I mean, in other words, is it reasonably likely that a survey like this could say, oh, a minority of candidates, less than half of, a minority of voters, like less than half of voters, like the candidate, when in fact 60% like the candidate, right? That's the kind of thing that like a pollster doesn't want to happen, or wants to know how confident they are about their predictions. And and 50% is actually an important number when we're talking about elections, right? That's why I'm putting 50 here. You want to know, like, is this person likely to have a majority in the population? Okay, but in this case, could the pollster conduct a survey and the survey reveals that less than half like the candidate? Well, we can calculate this question using the binomial distribution. And so to answer the question, we could calculate the probability of 0 plus the probability of 1 plus the probability of 2 plus, and keep going through 49. Okay? That's the perfect way to answer this question. Exactly perfect. You go through and you do each of those calculations. But that's 50 calculations that all have factorials with big numbers in them. It's a pain to do that calculation 50 times. Alternatively, we could use this fact that x is approximately normal. Well, if we're going, and then work with the normal distribution. But for that, actually, we need two other pieces of information. Like, we could solve this question if it were normal and we knew the mean and standard deviation, right? In other words, if we have mu, the mean, and the standard deviation, sigma, then we can use the fact that like x is distributed normally with a mean of mu, variance of sigma squared. Okay, I'm actually going to add a little note. I'm going to write the word or the abbreviation approx over that. It's approximately true that it's normally distributed. But we need mu and sigma. Well, we go back to the formulas that we have for the normal distribution. I'm sorry, not the normal, but for the binomial. For the binomial, mu, that's the expected value, is n times p. And the variance is n times p times 1 minus p. Okay. Well, we have that information for this question, and we can plug in values. So, for example, like to get the expected value, n equals 100, p equals 0.6. So this is 100 times 0.6. Okay. For the variance, n times p times 1 minus p. 100 times 0.6 times 1 minus 0.6. So the mean, mu, is 60. And the variance is 24. Does that sound right? Okay. So now, this question, what is the probability that x is less than 50? We can ask for the binomial, for the normal distribution. What's the probability that x is less than 50 when x is distributed approximately normally with a mean of 60 and variance of 24? And again, I'll write approximately normal. Okay, so now for these questions, remember the trick is to standardize the values. When you're dealing with a normal distribution, you standardize the values and then look up the standardized values in the table. So it's the probability that x, and actually I'm going to show some excessive steps here, but x minus mu over sigma is less than 50 minus mu over sigma. I'm just putting in that step to explain what we're doing and why the math balances. We're doing the same to both sides of the inequality in there. We're subtracting off the mean and dividing by the standard deviation. All right, so the thing on the left, x minus mu over the standard deviation, that's a z-score, less than 50 minus the mean, 60, over the standard deviation. So remember, the standard deviation is the square root of the variance. So this is over the square root of 24. Okay. And at this point, it's a matter of doing a calculation. Let's see, it's the probability of getting a z-score less than, and I believe this is negative 2.0, are you pulling out your calculator? No, 2.08, I'm pretty sure. Okay. And then we consult our table for the standard normal distribution. So let's see. That table looks like, oh, no. Okay. Here's the table that we want. And in particular, we're looking for 2.08. Okay, so we read down the column on the left to get to 2.0. Okay, so we'll be in this row. And then we read down the column for 08, for the hundredths place. And we get a value of 0.4812. Okay, so that tells us that the chance, okay, so there is a 0.4812 chance of being between 0 and 2.08. Okay, we're interested in knowing actually, okay, now this question is actually asking for the area below negative 2.08, okay, which is the same as the area above 2.08, which is 0.5000 minus 0.4812. And so we get an answer of what? 0.0188. And that's it. Okay? Scroll up a little bit, yeah. The O-looking thing. The thing that looks like a 6 on its side is a sigma, which stands for the standard deviation, which is the square root of the variance in X. Okay, let me do another example along the same lines. Let me pull up the normal table, even in the beginning. All right, so we will use this normal table, but a different polling question. Okay, imagine that the pollster surveys N equals let's do 1,000 people. And again, from a population where P equals 0.6 is the probability of a person supporting the candidate. Okay. What range is likely to, or yeah, what is, let me reword this. What is the middle 90% of the outcomes for X? Basically, this is like saying that this is finding a range of what's likely to happen for X, because you recognize that with 1,000, like if 60% of the population favored the candidate, you survey 1,000 people, you would expect how many of them to favor the candidate? On average, it'll be 60% of 1,000, right? 600. That's the expected value, by the way, exactly what I just explained. The expected value is calculated as the probability times the number of observations. Okay, so like 60% chance of each person favoring the candidate times 1,000 people who are surveyed. You expect 600 people will say that they favor the candidate. But randomness, that's what we're dealing with. You do not actually plan, or you would not actually get exactly 600 people each time answering that they favored the candidate. Sometimes it'll be a little bit higher, sometimes it'll be a little bit lower. Okay, so the middle 90% of outcomes for X, like what's a likely range for X? Well, we tackled these questions about the middle such and such percent of a distribution earlier. And for that, let's think again of how we did the standard normal. Okay, so we graph the standard normal distribution, and it's centered at 0. Okay, and we want a range centered around 0 that goes from negative Z star up to positive Z star. Range centered at 0, containing a total of 90% of the distribution. Well, really the way to solve this is by splitting up that 90% into the portion below and the portion above 0. We would expect to have 0.4500 down below 0 and 0.45 above 0. Okay, so we need to find Z star with the probability that Z is between 0 and Z star. We're talking about this range right here, right? The two sides of this are equal. correct? Okay, so if we find the z star on one side, it's the same as the negative z star on the other side. Okay, so we want to find this z star that gives us 45%. Okay, then we go and we look in our table. And so we look in the table for the value that comes as close as possible to, that comes as close as possible to 0.45. The closest is z star equals 1.65, right? 1.64 is fine, 1.65 is fine, anything in the middle is fine. There will be some tolerance for rounding errors on the assignments and test. Okay, so this is part of what we want to do. So let's see. What we have is the range goes from the bottom end is is z equals negative 1.65 to the upper end is z equals positive 1.65. And now we have to go back into the values of x. Remember that z stands for x minus the mean over the standard deviation. Okay? The mean, mu, is calculated as n times p. According to our formula, that's how we do it. And sigma is the square root of the variance. So it's the square root of n times p times 1 minus p. All right, plugging values in. The mean is 1,000 times 0.6, 600 people. Mean, expected value, average, they all have the same meaning.
So 0 is 600?
So, okay, so 0 is 600 in the sense of a z-score of 0 means you are smack dab at the center, yes, at the average value of x. So if your value of x is 600, and that's the average, then your z is 0. Yeah. Okay. And for the variance, this is the square root of 1,000 times 0.6 times 0.4, right? 0.4 is 1 minus 0.6. Okay, so it's the square root of 240. Anyone have your calculator handy? I can do this. 15.5. Okay. So the bottom, let's return to these statements. The range is from z equals negative 1.65 to z equals positive 1.65. This means that z minus the mean over the standard deviation is equal to negative 1.65. And on the upper end, I apologize. This should be x minus the mean. Z stands for x minus the mean. X minus the mean over the standard deviation equals positive 1.65. Tells us the upper end of the range. So x minus 600 over 15.5 equals negative 1.65. You see how we're going to solve this for x, right? Now we can multiply both sides by 15.5. X minus 600 equals negative 1.65 times 15.5. Then the final step, let's add 600 to both sides. So x is equal to 600 plus 600 minus 1.65 times 15.5. And we go through the same steps for the upper end. X minus the mean, 600, over the standard deviation, 15.5, is equal to positive 1.65. Multiply both sides by 15.5. So x minus 600 equals 1.65 times 15.5. Final step, add 600 to both sides. X equals 600 plus 1.65 times 15.5. Okay, and I see you're already working on your calculator. Do you have the two limits?
574.4 and 625.6.
Okay, so this is the range.
But what does that number mean?
Okay, what does that number mean? It means that essentially there is the best explanation is there's a 90% chance that the pollster will get an answer in that range. Okay? In this size sample with this value of p, there's a 90% chance that the answer would be somewhere within that range.
Really, you could just look at 1.65 times 15.5 and say, like, there's a 90% chance that you only get this amount of people wrong.
Yeah. I mean, this is trying to, yeah, there's a 90% chance you're going to get a number between 575,
Right.
well, 574 and 625. You know, at least like this pollster is going to know that it's very unlikely that they'll get less than 500
Right.
because they have so many people in their sample.
And if it was 10,000, the numbers would be closer?
If it were 10,000, the range would get even smaller, correct. That is true. Or, I'm sorry, the range would get smaller relatively. Yeah,
As a
relatively.
percentage,
Correct.
but not as a
Yeah. Yep. That is exactly true. It's going to be about 2 weeks from now in class.
Yeah.
Okay, so do you all follow this?
Are you going to post these slides?
I'll post these slides, yeah. Actually, I have already posted the slides from this morning's class, but I'll post these as well. So this is actually like really getting at what pollsters do. And they talk about margins of error. This is exactly the kind of thing that they have in mind. Like basically, another way of writing this would be that they expect the answer will be 600 plus or minus 25.6, right? And they could say that they are 90% confident with that prediction. Okay, again, this is going to link to things like margins of error and what we call confidence intervals for estimates. Okay, so this is the binomial, and there's one other distribution that fits the same like normal approximation. That's the Poisson distribution. So the Poisson distribution is approximately normal when the mean, the expected value, average number of events, mu, events is large. Okay. So this means that if we want to answer a question like the average number of customers at my store in a day is 25. Okay. What's the probability that in a given day I have fewer than 8 we read down to 1.4. And then for the zeros place, that's also 0. So we have 0.4192. Now maybe we should go in, okay, so maybe we should think about exactly what it is we're trying to calculate. I should sketch this out. Centered at 0, we're trying to find the probability that z is less than negative 1.40. Yeah? So we want to know the area out in this tail, okay, out at the end of the distribution. Now keep in mind, when we look up values in the table, we're told the opposite of the tail. We're told this value between 0 and negative 1.4, but not the tail. Okay, so keep in mind that this whole area below 0 is 0.5. We want only the area that I've shaded in gray. Okay, but what the table tells us instead is that the area in red is 0.4192. So the final answer to get what's in the gray area is going to be 0.5000 minus 0.4192, and what we get is 0.0818. Okay, that's the answer to the question. Probability of fewer than 18 customers fewer than 18 is equal to 0.0818. Questions? Yeah. 8% chance, yeah. Or an 8.18% chance, yeah. Okay. We good on this?